All right, let's start. It's a pleasure to have another one of our members seminar. This is a seminar for those of you who are visiting. This is a seminar of BIMSA, where faculty explain their own research. It's to help us learn about each other. Maybe we can learn that our research has intersection with our colleague in the institute. It's a pleasure to have Sebastian Heller, who is going to talk about algebraic curves and minimal surface.
So before I start, I want to say that I enjoyed the last talks very much and I learned a lot. So I think this BIMSA member seminar is really a good opportunity for all of us, the members of BIMSA, to foster communication and to really make BIMSA a place where great ideas can grow. So yeah, I would like to thank the organizers for letting me talk today. And I will talk about one of my main parts of research, namely minimal surfaces, from a certain complex geometric or algebraic geometric point of view. So you can think of that as some kind of continuation of Lynn's talk a few weeks ago, but my main focus is on minimal surfaces. So yeah, what are minimal surfaces? So we consider maps from some two-dimensional domain, maybe this abstract torus here, into space. And this might be Euclidean free space, it might be the free sphere, a more complicated Riemann manifold, or if you are interested in general relativity, some Lorentzian manifold. And then you consider the area functional, and you look for the critical points. So you look for those maps which are under first order variation constant for the area. And this gives you a usually nonlinear partial differential equation, which describes that minimal surfaces. So yeah, together with the length functional for curves and somehow the higher dimensional generations, the volumes, it's most likely one of the most natural functionals, at least in geometry. And you have seen its relevance in physics, sciences, and other applications in Lynn's talk last month. So I won't go into that any further, but of course, if you are interested in that, just get in contact with us. In mathematics, it used to play a very prominent role in the last 150 years, at least in geometry and analysis. For example, the first Fields Medal was awarded to Douglas for his solution of the plateau problem. So we will come back to the plateau problem later. And many of the constructions in analysis and geometry and geometric analysis somehow come from the wish of understanding minimal surfaces and the area function much better. And finally, I would say, yeah, they are just beautiful geometric objects. So I hope after the talk you can agree on that with me. So in Euclidean free space, there are no compact examples, right? This is similar to the case of straight lines, geodesics. If you look for the shortest curves between 2 points in Euclidean space, it's just a straight line. And if you continue that, it goes up to infinity, but never closes. In the free sphere, in the round free sphere, it's possible to close up. Namely, shortest curves are locally shortest curves, the geodesics, are parts of round circles, and they close up. And the same can happen with minimal surfaces. It doesn't happen all the time, like for geodesics, they always close up if you continue, but there are minimal surfaces which can close up. And the first non-trivial examples of them have been constructed by Lawson in the 1970s. So here you see some of them. So the first one, the left one, is of course the round sphere, which was known before. The second one is the Clifford torus, which was also known before in the 19th century. But all the other surfaces are new and have first been constructed by Lawson in that paper. And actually, there are infinitely many of them, and they are indexed by two integers, k and l. And these k and l refer to the symmetries of the surfaces. So let's not talk about the symmetries of spheres, but here you start seeing rotational symmetry around the vertical axis and a rotational symmetry around that axis. So the index refers to a k+1 times l+1 fold symmetry of the surfaces. So this surface psi to 1 has a threefold symmetry. And for this surface, you might expect a fourfold symmetry, right? But what's happening here is that you look at a stereographic projection into a Euclidean free space, the surface line in the free sphere. And by doing that, we break some of the symmetries, which means we just can't see them with our Euclidean eyes, okay? But it has a fourfold symmetry as well. And then there are some more complicated. So maybe that's a good point to remind you that topologically, surfaces or compact-oriented surfaces are classified by their genus. So there's only one of them of genus 0 with no handles. It's the sphere. Then there are the tori, which are all diffeomorphic. They are the guys with one handle of genus 1. And you have surfaces of every given genus. So meaning the number of handles can be an arbitrary, non-negative integer. So here it's 2, here it's 3, here it's 4, and yeah, so on. So in general, the Lawson KL surface has genus K times 1, just for reference. So how did Lawson construct these surfaces? So he started with a geodesic foregon. So these black lines here give us a foregon. So we have 4 straight lines in the free sphere, and they have certain angles here. And then Lawson looked at the plateau solution, so the least area surfaces with that prescribed boundary. And by the solution to the plateau problem, that least area surface exists in that cases. So let us see what's going on here. So you start with that geodesic polygon, and you look for the least area surface inside, and you find that, and then you can start rotating it around and reflecting across the straight lines. And if you choose that angle here, that angle appropriately, in the end, the surface closes up to give us some compact surface of a given genus. So in this situation, it closes up to a genus 2 surface, as you see now. Okay, so because there is this plateau problem involved and this implicit process of finding a minimizer, we don't have any explicit parametrizations or explicit knowledge about geometric data like the area of these surfaces, at least for genus bigger than 1. So we can do that for genus 0, of course, and for genus 1 as well, but not for higher genus, for none of them so far. But recently, with the collaborators Lynn and Nick Schmidt, who also made all these pictures, and also with Martin Trezé, we gave some more complex analytic proof of existence of these surfaces by so-called integrable system methods. So a few things are known, actually. For example, the index is known. So if you look at a minimal surface, which is critical for the area, you observe that shrinking the surface decreases the area, at least in higher order. And the index is the number of different directions where you can decrease the area in higher order. And the index of these surfaces has just been computed recently by Capoleas and White. So why are people interested in these Lawson surfaces, in particular in the Lawson G1 surfaces? So from my point of view, the reason is that they are really the best realization of a given topological type in space. So the simplest Lawson surface, Psi10, is just the round sphere, period. The Lawson Psi11 surface is the famous Clifford torus. So there's a functional, the Willmore functional, which is related to the area function. But it has different properties and is somehow more complicated. It measures how round a surface in space is. And opposed to the case of the area functional, you find in each topological class an absolute minimizer. You cannot shrink to 0. You always find an absolute minimizer. And the famous Willmore conjecture stated that the Clifford torus minimizes the Willmore energy for tori. And this was proven about 10 years ago by Marquez and Neves. And actually, they proved that the Clifford torus minimizes the Willmore energy amongst all surfaces of positive genus, not only amongst tori, but also for higher genus. And the Clifford torus is also, by the resolution of the Lawson conjecture, the unique embedded minimal torus in the free sphere. So this is really the best torus, I would say. And for higher genus, it's expected that these Lawson G1 surfaces are actually also the Willmore minimizers for a given topological type for the genus G surfaces. Okay, so what kind of results do we have for these surfaces? So the first one I'm very proud of, maybe not the first one, the most recent one I'm very proud of, is that result where we can get our hands on the areas of the Lawson surface. So we can express them in a certain way in terms of so-called alternating multiple zeta values. So I guess everybody knows the Riemann zeta function. This can be generalized to multiple variables. So we, instead of just having one integer n, we have d many integers, and generalize the formula here. And we can also make it a bit more complicated by putting some epsilon 1 up to epsilon d, which may take plus or minus 1. So if we do that, we get so-called alternating multiple zeta values. And later we might also generalize to complex values, but not at the moment. Let me just mention that for notational reasons, I will use that overline to indicate that the corresponding epsilon here is minus 1 instead of 1. Okay? So what we then do is the following. We start at the large genus G limit, G goes to infinity, at the limit, which is known to be two intersecting round spheres, as you can maybe guess from the pictures. And they have area 2 times 4 pi, namely 8 pi. So that's the starting point. Then we deform the genus. So if we do that, we get some kind of formula for the area of these surfaces as an expansion in the genus. So the geometric idea behind that is that we deform the angle of the fundamental polygon. So to be more concrete, we have that these two angles, this angle here and this angle, the opposite ones are pi half, and we only deform these two opposites. So if we do that, for example, with that formula, we deform the plateau solution, and also we deform the surfaces. So in general, for general T, you get surfaces with branch cuts, basically. But for special values of T, namely, basically, but for integers, the surfaces close up, as you can see here. So by doing so, we get that expansion, and we can get basically recursively these values in terms of these alternating multiple zeta values. So the first non-trivial coefficient here is just log of 2, which is minus zeta of overline 1. So if you sum the alternating sum, right? The next term is basically zeta of 3, a Perry's constant up to some rational number. So actually, the name comes from the fact that Perry proved that this number is irrational. It's a conjecture that all the odd zeta values are actually irrational, but it's far away from being proven. So one example proven in that direction is that among zeta of 5, zeta of 7, zeta of 9, and zeta of 11, at least one is irrational, right? But it's a really difficult business. So the next term is slightly more complicated, but we start seeing some kind of pattern. Namely, the alpha 5 is a sum of alternating zeta values of so-called weight L. In this situation, L is 5. So if you sum up 1, 1, and 3, you get 5. The 5 is just 5, 3, and 1 plus 1 is also 5. So you might wonder what happened here, but actually pi squared is up to a rational just zeta of 2, so it's giving 5 as well. And actually, we can prove that formula, even if it gets much more complicated for higher terms, right? So, yeah. This is quite fascinating, but we can also deduce some geometric properties from this theory. Namely, if we look at the formula, we see some kind of series, and we might ask, where does it converge? It looks like it converges up to genus 1, up to T is 1/4, where the value of the function must be 2 pi squared, the area of the Clifford curves. We don't know that, but we can prove that the convergent radius is at least 0.129, quite huge. And as a consequence, we can deduce properties about the area, but also other properties of these surfaces up to genus 3, basically, which is really good. For example, we obtain that corollary, which is, I guess, quite important in view of the Willmore conjecture, namely the areas, and therefore also the Willmore energies of these Lawson surfaces, psi G1, are strictly monotonic in G. So you start with 4 pi for the sphere, you have 2 pi squared for the Clifford torus. You don't know what happens for genus 2, but you know it's strictly increasing up to 8 pi by our proof. At that point, you might ask, wait, we just told that we can do things up to genus 3, right? So what happens with the genus 2 guy? So we can by hand estimate that the area is less than that area. And by the resolution of the Willmore conjecture, the area of that guy is bigger than that of the Clifford torus. So somehow, luckily, we can even treat that guy here in between our range. But that's just a remark for the geometers here. So why is it difficult to get some kind of information about these surfaces? And why don't we get our hands explicit on these guys, as opposed to what these pictures show you? So the main reason is that we don't have a systematic, or we didn't have a systematic treatment of these higher genus minimal surfaces. So this is different to the case of genus 0, where everything is known. So there's just a round sphere, nothing else, by maybe the first paper in the field of global surface geometry or global differential geometry. And in genus 1, Brandle somehow 10 years ago classified the embedded minimal surfaces to be just the Clifford torus. So in genus 0 and 1, we know a lot. And actually in genus 1, there is much more we can say. So there are also many immersed tori. So they have self-intersections. They're not embedded. But for them, we have a very good control. So they are given in terms of integrable system methods. So there's an associated spectral curve, maybe of very high genus, but in terms of algebraic geometric data on that algebraic curve, one can express all these surfaces of genus 1 by algebraic geometric or integral system methods. So things are quite different for higher genus. We have a few examples now by different methods, beginning with the plateau solutions of Lawson, by gluing methods of Capellaers, and recently by the min-max methods, which also played a role in the proof of the Willmore conjecture, mainly by Marquez and Neves. And also we have these integrable system proof of existence here. But there was no direct generalization of these integrable system methods to higher genus for a long time. And this was one of the main reasons why we are not able to get our hands on these surfaces and all their properties. So how do we do it now? So maybe let's, and what are these integrable system methods, or what are these integrable PDEs? Maybe let's start with the most general definition, but maybe not let do that. But let me just quote Nigel Hitchin, who himself is citing Louis Armstrong, answering the question about what jazz is about. So if you're going to ask, you will never know. So we don't care here for the definition of what an integrable system is, but we just want to focus on some of its features in this talk. These features are basically the existence of many conserved quantities and some internal symmetries of these integrable systems, or of the equations. And that was wrong. And the presence of algebraic geometry, which allows us to explicitly parameterize at least some of the solutions. So in my field of differential geometry, these integrable partial differential equations basically show up in very special situations. So you start with a very special PDE, which has some internal symmetries. And then you can reinterpret that as a compatibility condition for a family of linear ODEs in my situation, on our surface. So for a family of flat connections in more complicated terms. So examples of that, of course, include the Euler-Lagrange equations for the minimal surfaces in space forms or symmetric spaces, Zeka equations, affine Toda equations, just to name a few from geometry. But of course, they also show up everywhere else in math and physics, as many of you know, I know. So what's important then is that periodic solutions of that PDE. So if you have a closed domain, a surface which closes up, you look for periodic solutions of your partial differential equations, and then this gives us a family of quasi-periodic solutions of the corresponding ODEs, which depends on the additional family parameter. This family parameter here, which is usually called the spectral parameter. In our situation, it's usually just some complex number in not being equal to 0. Okay? So instead of showing any more details, let me point to a very classical example, namely that of minimal surfaces in Euclidean space. So that's basically a linearized version of it. And there you have the associated family, which comes from the Weierstrass representation. So you can deform the catenoid, the guy which closes, into the helicoid, that handle surface, by changing the spectral parameter lambda here. And there's some generalization to more complicated nonlinear PDEs and so on. But in the nonlinear setup, what you usually get is non-abelian monodromy, depending on our spectral parameter lambda. While here, in that classical case, we just have periods, so abelian monodromy, which is much simpler, of course. So you might guess at that point that the topology of the underlying domain of our surface is very much related to behavior of the solution. And actually, that's true. It's very much the same as happens for the geometry of surfaces. So if you ask what kind of constant curvature metrics you can put on a given topological surface, you get for spheres, genus 0, you just have the spherical metric. For tori, you have Euclidean metrics, flat metrics. And for all higher genus, it gets really interesting. You get hyperbolic metrics and the moduli spaces and all kind of stuff, which is, of course, very interesting. So we get something similar here. So in genus 0, the fundamental group is trivial, which means that we can shrink every closed curve on our sphere to a point, right? And as a consequence, all the monodromies are true. And then, by some very non-trivial work, by people like Uhlenbeck and many others, all these solutions of these corresponding integral PDEs are in a sense trivial. So they can be written down after a long process in a basically trivial way. In genus 1, it's more complicated. Not all of these solutions are trivial in that sense. Somehow because the fundamental group is not trivial anymore, but at least it's abelian. And therefore the monodromies, which a priori might be non-abelian, are reducible, and the solutions can be linearized. Basically, that's what's happening in this integral system setup, where we can parameterize the solutions in terms of a linear flow, which maps from the two-dimensional torus with the abelian structure into the Jacobian of the spectral curve. And in that way, we get a linearization of the equations. And we can parameterize the solutions quite explicitly in terms of theta functions and things like that. So for higher genus, the fundamental group is, of course, non-abelian. The generic monodromy is irreducible, and the solutions don't linearize anymore, but things get more complicated. So what are we doing in order to overcome that problems? So one of the basic ideas here is to look at some kind of compactified moduli space of these possible monodromies. This is usually called the Deligne-Hitchin moduli space. And in that space, we map our associated families of ODEs or of the monodromies of the ODEs, okay? These monodromies have to satisfy very strong conditions depending on the type of the integrable PDE. So just to name an example, if we look for minimal surface in the free sphere, the monodromy must be unitary in the obvious sense for unimodular spectral parameters. Okay, so let's not go into that anymore, but let's look at some consequences. One of the important consequences of that setup is that this associated monodromy curve determines everything of the solution, right? You have that algebraic, that complex curve, CP1, sitting inside that complex space, which determines your solution and all its properties, okay? So basically, the problem of understanding these minimal surfaces or other related integral PDEs reduces to understanding these kinds of complex curves in that moduli spaces. But of course, this is a difficult task because these monodromies can only be computed in very special cases. We have this Riemann-Hilbert type problem, which is quite complicated. But some idea, the more complicated the monodromy curve in that complex manifold is, the more complicated your solution gets. Okay? So how comes theta free and all that into game? So the idea is that not only the monodromy curve determines the solution, but also the geometry or the solution determines the monodromy curve. And therefore, in the case of very symmetric surfaces, like Lawson surfaces, we can express the monodromy curve in terms of the simplest that in actual Fuchsian systems. And here the residues, they depend on our spectral parameter in a very complicated way. We don't fully understand yet, but also they depend on our genus, or better on our time parameter. And by doing that, because the geometry is quite rigid for these Lawson surfaces, we can apply the implicit function theorem and prove existence in that setup by putting all the constraints we have. But something which is quite interesting, we can do somehow better. We can look at the implicit function theorem and solve it recursively, step by step, in the parameter in orders of t by solving finite dimensional linear systems. And this basically works as follows. We start with some with the residues, we expand them in time, and then we observe that the residues, the coefficients in t, they are polynomials in lambda as well, have some kind of structure. Okay, so we expand the monodromy in terms of iterated integrals. We express the multiple theta values in terms of iterated integrals, a thing which was first done by Kontsevich. And we put all together, and we are able in the end to express areas in these theta functions. Okay, so that's everything I want to say about these minimal surfaces here. The question is, are there any other applications, or is it just very special for minimal surfaces? But of course, there are others. So another nice example is that of the Hitchin moduli spaces. So we have the Hitchin self-dealing equations, and they give us some kind of correspondence, usually called the non-abelian Hodge correspondence, between algebraic geometric data, topological data, and differential geometric structures. And also, they induce some very nice and rich geometry on the surfaces, on the spaces of solutions. Namely, we get a hyperkähler space. So this means we get a Kähler space for 3 different anti-commuting complex structures I, J, and K. So examples of that are given by Calabi-Yau manifolds in even complex dimension. So what we can say, at least in special situations like the 4-punctured sphere, is again that we can express the Hitchin metric and this non-abelian Hodge correspondence in terms of multiple polylogarithms, at least expand them. So what we do is we start at what Andy Neitzke at least calls the infrared limit, but maybe some physicists from the audience can elaborate a little bit more on that. So we start at the limit t is 0. So t now plays the role of the so-called parabolic weight, but you can think of that again as the genus. And we do the expansion. And then it turns out the moduli spaces, they have nice homomorphic symplectic coordinates independent of the time. And we can express things in these coordinates. So for example, we can express the scalar potential, which contains all the information about the metric. So in terms of these coordinates. At that point, I should maybe say that it's a scalar potential for the complex structure J, while these holomorphic coordinates are with respect to I, but we can get our hands on that as well. So we start at T0, and we observe, or we see the Iguchi-Hans metric. So one of the first examples of hyperscalar metric. And then we start expanding in T, and we get more complicated terms. Is it me? I don't know why that comes up. Okay, so we start. We start expanding, and in first order we start seeing the conformal type of the four-punctured sphere already, and this becomes more and more complicated. So I won't write up the higher order terms. So something is not working anymore. Okay. My computer is frozen. Oh, no. Okay. So I don't write up the formula for the next term in general, but restrict to the most symmetric case and to the nilpotent cone. And then we observe again our set of free values. And of course, this continues on and on. I guess I should hurry up a bit. So another class is that of minimal Gaussian surfaces in Kähler manifolds. So Kähler manifolds basically combine in a wonderful way Riemannian geometry, complex geometry, and symplectic geometry. And it's natural to ask for classes of surfaces or submanifolds which are special for more than one of the structures. And a particular class of that is minimal surfaces with a Lagrangian constraint, namely they are minimal surfaces and the symplectic form vanishes. So they play some role. Some delay. Right, now I don't restrict, but to codimension 2 surfaces. Okay, yes, so now we are in higher codimension. In this situation, we are in real codimension 2. And these minimal Gaussian surfaces play some kind of role in mirror symmetry as well, as you might guess. But only one class of examples has been constructed so far, at least for higher genus, of very degenerate conformal type. So in a recent preprint in work, we prove the existence of a new family of these minimal Gaussian surfaces, which I think is quite interesting because the conformal type is that of the Fermat curves. So the Fermat curves are complex holomorphic curves in CP2 by its definition, but also they allow for minimal Gaussian inversions into the same space. And we can compare, again, their areas in Willmore entities. So the area basically grows the same kind of, like the area of the Fermat curves of the minimal complex surfaces. But actually, some of the Willmore energies are below, which is, I don't know, maybe interesting. So let me end here, basically, and just telling you what might come next and whether you might have some ideas on certain points. So, of course, I would like to understand this integral system flow here. So we get some representation, some Lux representation of that flow in coadjoint orbits on the loop algebra in lambda, but we don't understand. There's something going on in number theory. We get some nonlinear identities for multiple theta values. In particular, this holds true if we study the Hitchin metric. And that's quite fascinating, but we don't know why. Maybe I should just skip that. If you're interested in experiments, just contact me. And let's end with some geometry. So basically, the more complicated our curves get, monodromy curves, the more complicated our surfaces get. And here you see some bubbles on our surfaces. And the existence of these bubbles relies on the fact that our monodromy curves have some special unstable structures, which is some relation I really want to understand, but I can't prove anything about that at that point. So thank you, and I'm sorry for the interruption here. So yes.
Questions?
Yeah. So what is the degree of this Lawson surfaces?
Sorry, I didn't understand.
The degree of the conformal mapping to S2. Do you know?
Mapping into?
Well, the Lawson surface can be conformally branch cover over P1, right? What's the minimum degree?
Okay, the minimal degree of what kind of map? Sorry, I didn't understand.
Of the Lawson surface.
Over mapping to CP1.
Yeah.
I mean, it's
holomorph map.
It's a hyperelliptic Riemann surface.
They're all hyperelliptic.
I'm sorry.
You mean the Lawson surface are all hyperelliptic?
Oh, the Lawson G1 surfaces are hyperelliptic. The Lawson KL surfaces, K and L are both bigger than 1, not. That's not. So
what is the degree?
The minimal degree, I don't know. I mean, it's certainly at most K plus 1 or L, the minimum of K plus 1 or L plus 1. But yeah, I haven't looked at that question. I guess it's not too hard to find out. So one knows the full symmetry group, and maybe using that, one can quite easily determine the minimal degree. So yeah, I will have a look at that.
Well, what about the first eigenvalue of this Lawson surface? Is it equal to?
Yes, I mean that was actually one result I dropped in that talk. Sorry, it was proven somehow 10, 15 years ago by Sorey and Cho that they are embedded by the first eigenvalue.
Okay, if it's equal to, there's a inequality between the first eigenvalue and the area. Then proved many years ago. There's an inequality. Could you check the inequality? How sharp it is for the Lawson surface?
I mean, now we know the first eigenvalues by the other result I just mentioned, and we have good control over the area. So yes, we should be able to check that formula. And of course, I'm happy to.
Well, it's not formula. It's an inequality. I want to see how close that inequality is.
Yes.
The best possible.
So
lambda 1 divided by the degree. Lambda 1 is less than equal to degree divided by the area of the surface. Basically, that's inequality.
Okay. Yeah, we should look into that, and yeah, from our results, it's not so difficult to, at least for hygienists, get something meaningful out of that, and also generalize to all these KL surfaces. So we will get in contact with you. Okay.
Also, I think they forgot what Lawson they could. How did he know the surface that he constructs the embedded?
Oh, from I mean, you bound that in that fundamental domain. So you have these areas by the geodesic two spheres bounding your polygon, and the fundamental piece is contained in there. So it must be embedded. While I mean,
why is it embedded? Why? How you solve the plateau problem? How did he know it's embedded? We know it's true, but how did he prove that?
I mean, if I would approach that problem now, I would just use the Li and Yao inequality for the Wilmore function. So we know the area is below 8 pi for these surfaces, and they must be embedded. But I mean, Lawson did differently, and yes, he started with the fundamental solution and of the plateau problem, and I don't know who originally proved that, but in that case, that piece, of course, is embedded, and then he has the barriers and the symmetries of the surfaces, so he can check simply from the symmetries that the whole surface is under.
And by the way, maybe just historical, I should tell you, Calabi was the one who invented this construction, and Lawson carried it out. But Calabi doesn't care about the credit.
I didn't understand. Oh, Calabi.
Lawson's surface, the idea was actually due to Calabi.
Ah, okay. So, yeah. As I said in the beginning, it's a great place to learn something here, the seminar.
Yeah.
Okay.
Very nice talk.
Yeah.
Thank you very much.
Yeah. I want to ask you, you told us that you used some kind of integrable models. What kind of integrable models you use and how you use?
I mean, I represent these PDEs as families of flat connections or ODEs, and I just look at these ODEs connections, and then I mean to reconstruct the solutions and things like that, I apply generalizations of these theta function reconstructions, basically loop factorization methods and things like that, to obtain the results that the monotony curve contains all the information. So in that sense, but I mean, yeah, for higher genus, you don't have this linear flow, and it's not really clear what you do. But I mean, at least the one thing we know is these monotomies contain the information, and we can reconstruct things, and we can see areas and all that. So in that sense, I would say it's integrable system methods. Yes.
So maybe I ask you a question. If I have the sphere, 3-sphere, so how is the geometry of the surface you get related to the angles these lines on the sphere make?
I mean, a lot. Yes. I mean, depending on the angle, you get different topological type, you get different areas. So, but in a certain sense, our idea now is that these surfaces and similar surfaces like how you think of Stirling surfaces, they are the lowest energy. So basically, they are the higher genus vacuum solutions. And then the surface I showed last, they are still on my computer, but not shown anymore for some reasons. So they are higher, they are somehow higher order energy solutions.
So my question is exactly related to that multiple bubble picture that you showed. If I embed this surface in a sphere with fixed volume, if I increase the symmetries, which somehow probably translates to the angles between these lines, or I increase the number of lines, probably I will get a minimal surface. If I keep doing this thing, increase the symmetry, the area.
What's going on there? Not really, I don't know why.
So if I increase the symmetries, area of this surface should drop, right?
If I increase the symmetry,
in fixed volume in sphere, area of the surface indeed should drop.
But you cannot do somehow change the constant mean curvature constraint and.
But I'm just using the fact that the volume of the sphere is fixed, and these geodesics are on the sphere.
You mean the volume enclosed or the?
Yeah, enclosed, yeah.
Yes. So, but I mean, and change the symmetry. So
yeah.
Change the genus.
So my question is, if I do this repeatedly, can I? Because your areas are written in terms of multi-value zeta functions.
Yes.
Can you say something about zeros of this zeta function?
Would you believe me if I say yes? No, obviously no.
Maybe you can actually approach it that
I mean, I just know that you cannot always increase. I mean, by experimental observation, for having more and more bubbles on them, you cannot arbitrarily increase the symmetries for a given conformal type. So it degenerates in a certain sense, and the solutions won't exist anymore. So I don't know the reason for that, but that construction doesn't work for all.
So if you increase the symmetry, solutions don't exist anymore?
Don't exist anymore somehow at some point. There are some, yeah, I don't know why. It's just observed experimentally, but yes.
Any other question? I have another question.
Well, actually, I wanted to ask you some other questions. For a long time, I suspect the eigenvalues of the Laplacian for embedded minimal surface should have arithmetic meaning. I wonder whether you can calculate the high eigenvalue of the embedded minimal surface, the Lawson surface or not. Would they be the high eigenvalue related to the theta function and all that?
So we haven't worked that out. What we know is we can, at least in principle, up to really working out the details or computation in detail, which become more and more tricky, of course. But in principle, we can expand the metric to higher order terms. So in lowest order, we see basically the two spheres, and then at the intersection, we see the desingularization in terms of the Church surfaces. And we can as well do this in higher order, but it becomes more and more tricky and more involved. But from that, we should not only see the areas, but also the Hopf differential. And if we work harder, the induced Riemannian metric. And with that knowledge, it might be possible to say something about the eigenvalues. So yeah, of course, that's a good point. One should definitely look at that and see how the eigenvalues behave for large genus, the higher eigenvalues of the Laplacian.
Could you just do numerical calculations?
I'm sorry?
Could you just do numerical calculation by calculus or relation? Minimax to calculate the eigenvalue. At least the first few eigenvalues.
I don't know, but I wouldn't think so that you can, I mean, really compute them more.
Well, not all. I mean, I'm just calculating, first 10 or first 20 eigenvalues.
So yeah, I can't say that at the moment. I just can say that it looks promising to use our approach to get some more information about these types of questions like eigenvalues or other quantities. Yes. So, yeah, working out something explicit becomes computationally quite hard, I guess. So we haven't been able to do that explicitly at the moment.
Okay, so one last quick question. You had the alpha case which were expressed in terms of zeta value, right?
Yes.
Do we know like explicitly what form each alpha k takes? Because it seemed as if you were writing it as a polynomial of, let's say, in terms of you take an n and then you partition n, and for each partition you have a term. That's what it felt like. You just flashed the slide. So do we know something more about that?
We don't know enough about that. I mean, we have a bit of knowledge, but not really. So actually, we would be quite happy if there are some ideas from physics or so which tell us what might be going on, because we don't know at the moment. We just know there are sums of weight 2k plus 1 alternating multiplicity values. Sorry. Yeah, and many of them don't occur at all. So only some of them we have some kind of version of saying which might occur and which not, but not really. I mean, we can compute recursively, but we cannot say what exactly in high order. Yes, not at the moment, but hopefully, maybe at some point. Yes.
So a very quick thing before we finish today. One thing you said, connections between algebraic geometry. When you look at solutions to these integral PDEs, of course, it's a consequence of complex algebraic geometry that these solutions eventually will give you these minimal surfaces. Yes. So you have a moduli space of these Hessian pairs, solutions, vacuum space, as you said, these differential equations, and then you have a moduli space of these minimal surfaces. But this algebraic geometric connection doesn't tell you anything whatsoever about the area. Am I right?
A priori not. Only if we bring in this Riemann-Hilbert type stuff or iterated.
So in order to estimate these areas, you kind of didn't use any algebraic geometry.
No, not yet. But yeah.
Any other questions?
Ask him if you can ask.
So if I look at these two-dimensional surfaces embedded in S3 as, let's say, solution of classical solution of an action of, let's say, a scalar function, because it's codimension 1. So you have a scalar function which describes the shape of this.
Yes.
And these are some solution of an action. And the integrable model you mentioned is the integrability of that action. Is it?
Yes,
is it
right,
what you
right.
said? And what is that action? Is it like?
I mean, in
action?
S3, it's the nonlinear sigma model. It's somehow the nonlinear sigma model, the conformality constraint. Yes.
All right, if no more questions, let's thank the speaker again.
Well, this is a good member seminar, I guess. We learn a lot from you.
But I'm happy about it.
Mhm.
Happy about the technique that is in the job.